This is the Earth, and this thing to the left of it, that's a star. Today, I'm going to be using this star to heat up the poor Earth to see how much heat this planet can handle. But before we do, how much heat do you think your city could handle? Or just the Earth in general? A lot? A little? See if your guess is on point or far off. And to be honest, I think a good start would be to make our star actually pretty cold. By pretty cold, I still mean the temperature of the sun. Why do I say this is pretty cold? Because compared to some of the temperatures that are gonna be in this video, the sun is nothing. It does not compare. So what is this sun here actually gonna do to the Earth at this distance? Great question, and I'll show you that. It starts off normal for the first 0.1 seconds, and you'll see it definitely starts getting really hot, and it's gonna spread and it's gonna spread, and eventually it's gonna cover the whole face of, well, at least this half of the planet. But it is really cool though, especially if you were like looking from the side when you can see like everything. It's kind of disgusting. I mean, would you be alive right now in this situation? Like maybe if you're over here, I feel like maybe I'm somewhere over here in America, so I think I have a chance actually. But if you're in the back of the planet, you're definitely alive right now. And this, however, does not fulfill my criteria, completely obliterating the planet. And you're gonna see later, when I mean obliterating the planet, this is nothing. For the considerable next 1,000 degrees of temperature, really nothing interesting is going to happen. It's just like the last time, but it's going to be more and more amplified. But there gets to a point in temperature where something really interesting can happen. I'm going to move this far away from what I'm about to do. So this is what I have right here. And this star is a nice and healthy 13 million degrees Kelvin, which is actually roughly the same in Celsius. It's still 13.6 million degrees Celsius. In Fahrenheit, that's roughly 24 million degrees. Very hot. And if you remember correctly, I was telling you something interesting happens at these very high temperatures. Well, it's something called stellar winds. When a star of this heat, given with its magnetic core, whatever it is, it actually will blow a planet away. Literally, it will blow the planet away with its heat. Luckily, the star is kind of small, and it's also kind of far away. So from this distance, it's actually not gonna have a huge impact on us. It will blow the continents around, literally, as you can see here, but its impact on the Earth as a whole isn't anything ridiculous. Yet. There's two things we can do. We can move this star closer, or we can make it hotter. For now, I'm going to move it closer so we can make it hotter later. Now, the star is actually pretty close. What's it gonna do? The same thing, but a lot more ridiculous. Let's watch it from the side first. I do say though, our whole planet isn't quite destroyed, so we do have more to go. And let's actually watch that from the front so we can see the main impact it has. It's really hot. That's the core actually, because the rest of this is getting blown away. And at this point, we can just go ahead and move it. It's really close to the Earth, and our planet is blown away. You probably didn't believe me when I literally said blowing away, but it literally gets blown away. There's no other way to describe this. But we still have some room to go. This is the surface temperature. We can crank that up a lot. So I've turned this star's temperature up 10 times more. So now we're at 130 million degrees, which this is not going to be fun. You can see this is 10 seconds into the simulation, and the front of the planet is torched, literally. And then it starts to push the planet backwards inch by inch. And we can just watch this as it happens because it's so cool. And then it blows the planet away. And all of this was in under 2 minutes. So this is just about real time. You're watching this. In fact, this is what it would look like if it was real time. So this is 1 second per second. So everything you're seeing is as it would happen in real life. How long does it take for you to not survive this event any longer? I think by now, most of the viewers probably aren't alive. But if you did, let me know though. If you did survive the 30 seconds of this, let me know. I'll multiply this by about 3, so this is 300 million degrees Kelvin, about 600 million Fahrenheit, and this is real time. So this is 1 second per second. So we all just eviscerated in like 2 seconds. And this is 10 seconds, so if you didn't get eviscerated in 3 seconds, you got eviscerated in 10 seconds. And then, oh my, our planet is like blue. It's blue and white. It's so hot, it turns blue and white. And we can watch as it actually will blow the entire planet away. That's the back half, so we are definitely gone. 30 seconds. You got 30 seconds max, and you're gone. That looks so cool though. At this point, I just want to see how fast I can destroy the planet. This is 1 billion degrees, and we are just gone so fast. I want you to guess, how fast do you think the simulation is running right now? 1 second per second? 2 seconds per second? That was 10 times slower than real time. I have it set to real time, and it looks like this. That is as fast as it would be if it were in real life. But I think the most interesting case is when this happens in real life. This is a real star that I've put the Earth next to, and when we let this run, I'm letting this run at 3 minutes per second here, we can see what would actually happen in real life if the Earth was next to a star that was 13 million degrees Kelvin.